We now come to the final part, part 4 of gravitational fields. We're going to start by looking at geostationary satellites. Now, a geostationary satellite is one which orbits the Earth once in every 24-hour period. But we know that the Earth also spins on its own axis once in every 24 hours. So what this actually means is that the position of a geostationary satellite always appears to be constant. In other words, it always appears to be in the same position to someone viewing it on the Earth. So if you saw the satellite directly overhead in a morning, then it would continue to be overhead, regardless of the time of day. There are advantages of geostationary satellites. For example, your satellite signal for your TV requires a geostationary satellite to send a signal to your satellite dish. If the satellite sending that signal was not geostationary, then you would constantly have to keep moving your dish in order to receive the signal, and that would make TV viewing impossible. Let's move on now to gravitational potential. So gravitational potential at a point is the gravitational potential energy that a unit mass, in other words 1 kilogram, has at that point. Gravitational potential is 0 when you get to infinity, and it becomes negative as you get closer to the Earth. So gravitational potential is the gravitational potential energy, or the work done, per unit mass. Let's see how that fits into some equations. So we've said it's the work done per unit mass. Well, let's think of an equation for work. Work is equal to force multiplied by distance. We know the force is the gravitational force, given by the equation F equals G m1 m2 divided by r squared. And if we were to have a satellite and we want to find out its gravitational potential, then the distance is also the radius of its orbit. So to find the work done, we multiply the force by the distance. Now remember that gravitational potential is actually the work done per unit mass, so that we then need to divide that by the mass of the satellite. So that gives you the equation that gravitational potential is equal to minus Gm over r, where m is the mass of the Earth. Now the gravitational potential difference is the energy needed, or the work done, to move a unit mass from one point in space to another point in space. So we can also say that the work done equals the mass of the object multiplied by its potential difference when we are moving it from one point in space to another point in space. Now, close to the Earth's surface, we say that the gravitational field is uniform. G is constant, m is the mass of the Earth, which is constant, and r squared, if you stood on the Earth's surface, would be the radius of the Earth, so that would also be constant, and that gives us G, which is equal to 9.81 meters per second squared. And as long as we don't go too far above the surface of the Earth, we're not really going to increase r significantly, so we can say that G is constant. We also know that force equals mass multiplied by acceleration, and that the acceleration is caused by gravity, so the acceleration is equivalent to G, so force equals mg, mass times the gravitational field strength. And if we move an object through a distance, let's call it h, we can say that the work done is equal to its gravitational potential energy, which equals the force multiplied by the distance moved, so that would be mass times G times h. And from that we can see that G multiplied by h must be the potential difference. That is the end of part 4.
Created using Powtoon.